of course, he wants this to be a desirable living unit. So what we are envisioning here then is a row house sized building, about 50 people. And you know where the row houses are over on Mayfield in that area. They're typically 3 stories. Here we have a basement, and the basement would have this laboratory. We have extensive metering of the building systems like air quality, what's happening in the rooms in terms of energy use and that sort of thing, and a lot of monitoring of the building as a structure itself. And we want this sort of constant interaction and outreach with students and visitors as well. So part of the challenge here is to explain and demonstrate exactly what's happening in the building, but at the same time not being too intrusive with respect to the people who live in the building. So this is activity that started about 2.5 years ago at a retreat of our Department of Civil and Environmental Engineering, where we embraced the idea of engineering for sustainability as sort of a vision or goal for our department, sort of a unifying theme. And one thing that came out of that retreat was that it would be good to have something on campus that would demonstrate what we mean by engineering for sustainability in terms of the built environment, the water environment, and energy. And so we came up with this idea, well, maybe we could have a different kind of a dormitory that would be an example of small-scale innovative energy and water systems. It would be heavily censored and monitored, and there'd be some things in this building that would be relevant to the less developed countries. We had a debate actually about should it be something that would be heavily that could be put in a less developed country. We decided no, but rather some of the things that we're doing here could be transferred. And our mantra here is sort of change live by where you live. We want this to be a focal point for innovators. So let me point out a few people. Dearline Associate Chair, Joel Schwischer with the Rocky Mountain Institute, Gil Masters, Emeritus Professor, knows a lot about energy. Architects here like Brad Jacobson, who works at PhD in San Francisco, Martin Fisher, Professor in the department. Others, Mario Curmio from UC Berkeley, John Cooney from Berkeley, and the like. This gentleman works with McDonald Associates in Virginia, well-known from designing green buildings. And we have students here, there's Lauren Dietrich and others in the picture that were involved in this retreat. So the students, faculty, and architects, and some experts to sort of brainstorm what this whole building would be like. Then following that, in winter and spring of that year, that was in the fall of the hotel floor, students under the mentorship of Gil Masters took some studies here to look at energy and water use currently in row houses. I guess in engineering, if you want to manage something, you have to be able to measure it. And we like benchmarks. So we want to get some benchmark data. Well, what's the current energy use in all the current? Another goal of this the student project was to get some idea about what kind of systems there might be and what kind of water usage systems there might be and how these might work together. So that was a student project, and then in the spring, that we continued this by looking at how the energy and knowledge pieces might work together. It actually gets a little complicated, and there's necessarily a clear answer here when they're all done. And in terms of the water management, we wanted to sort of get an idea of what's possible, what could we get away with in terms of the county, what might be possible in terms of demonstrating the spring of 2004. Now, let's pause for a second and look at some other buildings of this type where there are so-called green dorms. Carnegie Mellon University in Pittsburgh, it's about 260 beds, a lot big dorm, and some others have applied for this environmental design. And if you do a certain good job in terms of waste, like divert waste in landfill and that sort of thing, systems here that save energy, the building can fly gold and silver ranking by these things. So that's interesting, but it doesn't teaching static. Now this is an echo because it shows this native plant taste for shading and the like, and all of that is, and do these things in our green dorm as well. Well, what about here? This is how architects normally build. If we were to say, let's take Robinson House and this is a green meeting room. So what's lacking? Not the technology here. Engineering system, and it's not active. What we have in mind. Something that's due. It's mainly an academic building here, but it has living space for about 11 students. And the idea is to create certain energy efficiency systems. Brad Jacobs, and he had a group of last winter on green project, and they moved from the Pino over to on the first grade. And so there were like 4 or 5 student groups, and each group had sort of a different take. They envisioned this green dorm might look like living space, something that you could see like waterfalls, like synergy or a boundary. But these nice interest for the building in terms of presenting this in Trogo. Another example shows sort of a natural cooling district down. This is something like what the Carnegie Center for Municipal Ecology sort of inspired by that. 2 buildings here, and here you can see library with a green. When I got dorm to the provost last spring, things stopped right here. Something was really interesting in growth. And I don't know, except maybe there's been these kind of things at Stanford. And usually when you think about leaks and that kind of stuff, and here you're going to put a lot of help. I have a question about how does that feel in? We put in parking garages, you know, but you want to be really careful before you something look like that. You want to last for a long, long time. But that's an example of an approach. So this, we got permission to proceed with what's called the scoping of the study. But at this point, the project really became routine-wide. Everything up a year ago, I guess. Everything up to was student projects and some faculty and civil and engineering proposing it. But this summer, this thing sort of this into a project that was approved by the University Planning and Architecture Office, and it gets on their radar. It's on their list of actual projects and the like. And this little thing here is what they call a heartbeat diagram. I've got this an interesting schematic to sort of show the building process here at Stanford. But the first done here is you do a scoping study, and that means you just try to rough this. What is its objective? Where might it go? What might it cost? It might take about 6 months to do, and then there's a discussion about it, and approved. It goes on to the feasibility step, the first step in actually designing the building. The activity here sort of rose to the level of the integration with the new study. And at this phase, a lot of people are involved. These are faculty in civil and environmental engineering. The studies, you see their names here. These are people from facilities and the School of. Now, Jim Summers, the dean, pays for the scoping. These are land and building staff. Ruth Todd is the associate architect of the university. Laurel King is the sort of champion of this project. Happy, the landscape architect. And then dorms here. I'm doing very little, except when I visit them like this, or I come to vote or something like that. Well, dorm works and functions and how efficient properly and all that. So you need people from housing and building up. So that's the people interacted with. And we discussed 2 sites where this building might go. I live on campus over South Sierra, and I look back on this Mayfield Playfield. And I know about the Lord, there's a sort of a big empty lot back here. This is their end, there's a big, somebody sort of beat up here, you know. And I thought, wow, great place for a dorm, for this dorm. And the lot was so big, they could do there was demonstrate organic gardening and using recycled water waste and stuff like that. So that might be a possible site. Here, this is where Mayfield curves, and it's right across the parking lot from the right behind that. And so this ended up being the most favorite spot. And the reason here is that it's close in. And we want to be able to use this dormitory for demonstration, maybe classroom presentations and the like. So, over here, you're about as you can get to the campus core without actually, sort of being on the clock. This isn't that far away. Maybe it's taken or something. And in terms of just visibility, probably wouldn't work so well. Also, right up there, and from Mayfield, you can see it from the club and that kind of thing. So both for visibleness, we thought that's a preferred site, and the university has identified this area right in the parking lot here and the like, has already designated that as a possible site for not inconsistent with the use. That's sort of the area. I don't know if you were around when we had a temporary office, but that's kind of where. So, this is what Laura Goldstein does at the architect's office. We talk about dorm, and they say, well, a dorm has a seminar room like this. You gotta have, I don't know what a room. Do people have a room here? I think that means like a pool table or something, and here's a rec room, or some kind of, maybe a weight room. You gotta have a kitchen and a pantry, a dining room, student rooms, manager, and stuff like that. So without even really knowing exactly what the farm would look like, they'll say a typical 50 students got to have all this stuff. The ways to optimize it, like that pool room could be merged into the lounge or something like that. But when they think of a dorm, they list out here's a tea room and that kind of thing, have storage and so that. They haven't built a row house here last, so we're not too sure the spreadsheet analysis will actually be all done. What they ended up with was about a total building here, like 13,000 square feet or so, but you're going to have to add on this lab. There's 14,500 for a residence, another 4,500 for the lab. So it's about 1,900 square feet. Now that's bigger than a normal row house because we have and teaching level. That's what the people in the architect's office do. So they get an idea about what it's about. Then they go and they say, well, how much I know this standard cost that they use. Now they haven't built a row house, they built other dorms. So some square feet, architect fee, and all that kind of stuff, this thing out. And they ended up with like $9 million. To build it, something like a lot. But to build that, money paid not enough. Because remember, we want to be able to exchange energy systems in this building. We have water treatment systems to take that. So I think what we need $1 million for an endowment. What that endowment would do is provide for system maintenance, improve and exchange, get it really work right. We have to sort of be running this facility like a lab manager in a way. But I think when we're all done, we're probably looking at $1 million. That's my guess going to be for $2 million or more of that endowment. Now, I'll show you some other things in a little bit. I went over this summer with Prince and Mechanical Engineering, and I want to get one of these hydrogen. I'll show you a picture of one. Well, that's $1 million there. But our hope is Honda will give it to us. Anybody that lives there can drive it, but those are also off the chart. Now, what you just saw is the way that came up that building. And just like buying a car or something, you tend to focus on the sticker shock. And you say, well, wait, really, I'm going to cut that. This is the construction cost. How can I whittle away at I don't know how I'm trying to make that a smaller number. Now, we don't think that push here the way it can normally cost. You should be thinking of the sticker cost here. You should be thinking of the life cycle cost. So you build things, you hope it lasts here. What is operation and maintenance, energy efficient, save electricity, and you can use that to affect your so the total cost of the build, amortization, the construction cost, and we normally kind of want it down here. Our objective here, though, is you would take and do building in sensing of the kind of system and think about technologies that are this building standard in earthquake country. Is not that we would things and put it back in the building, but when we're all done, we want to be back up here in what it costs. We don't want to run that city It can't be replicated. You could imagine anything that was sort of connecting with evil, that no one else could do it. We don't want that. Let's look a little bit about energy here. This is sort of shows the energy use in the now attention. Education. This is why energy attention in terms of overall the energy used in buildings. Whether that's in commercial building, modern energy, that's the energy actually to build the building, yield, and that kind of thing. Our attention, we really want to do something about it. We have to build, and roughly, energy used per student. This is what now we did. Energy per student is $1 per year, a year, and this is various per Stanford. And this doesn't correlate exactly to the word. So there are short. But that's all my okay. This is that we are going to build a new one. We want to do better than me. So we better do better than me. That's what people pay attention. And what technology is at here is so that we use electricity. We're interested in sort of the net. The idea here is sort of net out, zero. And so the way this works is that the photovoltaics will generate during the day. And you have to take the areas to cancel out on a annual. So our goal is these systems will have. We're not going to take any energy right now. The way this is you look for energy, like for electricity. So what is happening? You take the photovoltaic, you have a condition, you convert it to AC, you put it out on the grid, to take back, and get out here. Come to Big Bang. And there's some interesting games you can play here too. Particularly summer, here, that's when people turn on the air conditioner. And if you put out on the grid, then you can take back from the grid nice price of electricity. You can actually do that kind of calculation with that. We talk about a green roof. There's quite a fair number of reasons to do this. To the cooling load, you can increase the bring on the roof. You can manage irrigation. It reduces this urban heat and you get in a concentration of buildings around. Everybody says it's being extra hot. For those here that know that number, there's 100 and more. So we're experimenting with that. Another one that's kind of interesting to look at is ground-coupled heat. And one way to think about a heat pump is you take 100 units of fuel, you run it through a power pump, you get 33 units. This electricity then surround the ground to run a ground. With it close, we're going to give about 120 units. And we'll put a heat pump here. They're actually being there for the dormer. That's one way you could put a point of running it with electricity you get from the grid. You burn your 100 units of that. This is in that heat pump from the grid, cell in the basement. Now, fuel cells, methane here, you require, and then you use the hydrogen in the fuel cell to come out of the water and CO2. Yeah, if you want to keep about 13 of this thing, about 35 units of electricity. You got to think about a fuel cell that would do that and dorm away for 6 hours. And I'm and then it's a kind of energy thing. Now, this fuel cell is basically you need to work. Now, so you get to 35 units of electricity. You have a unit 50 plant. It would actually take 120 units of a pump. And that way, you that all, really have a little bit. With a furnace or something, it was 10. But it has a source of both of them, it can save a lot of energy. So that's the idea. Now, if you really run a heat pump, what happens is that take 35 units of heat here, you run your ground pump, it's the heat, as you get 100 units of gas energy. So it's a little tricky to think. One of the things you want to test at this green dorm is the side basement and ground heat pump and the waste heat. That works together. Not a map, PC. I will this summer. R&D and really, they both have hydrogen carbon. That's the thing you see in the movie with the big bang flat and it drives along and everything. And the whole track down, we're not regular race car drivers, so there's other cars out there. And then they let us get a car around the track. That's 90 miles, they got us at 90. But when you go around the first line, those curves that look like that, I got 200 or something miles an hour. Take a seat. That's fun to do. So, here's Honda is doing. They think the route is a hydrogen powered. So they make a hydrogen fuel cell and use the fuel cell to use their cars. So basically, an electric car by hydrogen. That's not structure in the U.S. for hydrogen. And fuel cells are pretty basic when you have a bunch of college students. You have a fuel cell, you can waste heat and stuff like that. It's not going to get an energy to there. Now, where does this hydrogen come from? One is from the natural gas one, and change it up. Or you could put a plate on your roof or something different. This idea, because you're going through two energy conversions here. You get electrons, that hydrogen put back into electrons again, and that's not going to be very efficient. Interesting, an all-electric vehicle in hybrid. Now, a plug-in hybrid would be like a Toyota Prius. Well, when I was at Honda, I couldn't say Prius. I had to just generic electric vehicle. But you take a Prius and you put it next to it. Is that you have something like a Prius, eventually running around cities. All your short trips, 5 miles, something like that, would be all electric. Now you recharge batteries, so you can get enough rating. But you could use that for those. But I think there's a lot of potential there. That Hill is really good at doing envelope functions to estimate savings here in this dorm. This is where the element we have here. It's like kilowatts on natural gas, kilowatts on heat. We have a garage space. This is just maybe a couple hundred square feet. And that is the property that you could put 25 to 35 miles strips. All that's here to help more hot waters and more cold stuff here, so that your electricity during the day. And you have lots of other features in terms of environmental relation, earthquake safety, and stuff like that. But if we just look here at the energy bill, this is the most expensive door on campus now, $3,000. Now this is column bay. Now we certainly want to be able to do better in column bay. So we think it's probably about $5,000 each. And so we might save about 75% about organic row housing centers. And that's something we go and reinvest. And if you look at it, there's the Army's row house, and what the green dorm would do is we have 5% in terms of carbon emissions, more photovoltaics on the roof. And this is something the architects have on. Put up 30% on net zero greenhouse gas emissions. And that's something we want to study. Zero on electricity and zero on greenhouse. So what we're getting more electricity than what we're using, we're getting the credit for that because we are using a bit of methane. That's how you do it. We're thinking of water for irrigation and the like, and sort of a tiered system where you make that water about sink water for that irrigation. Eventually you can take the black water and upgrade that too, and also get energy from it. Have some might work. I'm going to skip the next slide here. And just one last slide here is something to word in the summer. Talk about fundraising for look at the feasibility study. Okay. Here's some of your recommendations here. Emily, Leslie, Dee, and Gerald, and the like. And it's a new crew here. This person and this person are from San Francisco. That's actually this guy here. This firm, EA group that designed the Monterey Bay Aquarium, and we're bringing for global ecology. So they know something about museum-like spaces. They also know a lot of as well. And is the mechanic of them. The maker here is a new professor in our department who has a background in the process. Bruce University architect, Laura Goldstein. So we're in a feasibility study, and what the technical charge was actually designing the look and feel of buildings and taking it all the way sort of working drawing but construction. So from this you could cost estimate. And also you figure that you go to your conservation. So this is just about building. And we're meeting tomorrow, bi-weekly meetings every couple hours over on Sarah Street. Talk about the design, look at what they are coming up with, and different faculty and other people are coming in to talk about what they would. There is the structural engineer. They're interested in how the foundation works and how you can use this building to demonstrate earthquake engineering, for example. There is the sort of our waste heat for generating bioreactors and how you can take like that and produce both methane for energy and the suitable for. So that's kind of where that's for the team and kind of where we are. To me, this is a project that is really pretty interesting. At a retreat, it's probably going to happen for people who probably have to actually, when construction starts, it'll all be done. That's where I can answer any questions now.
I was wondering about the hydrogen. I heard somewhere that, and I know that this is related to the whole goal of Enviornmental, but it seems like it would take energy to begin with to actually get hydrogen, whether you're doing electrolysis or starting with. Do you know of any way to figure out how they could get, and it seems like they're going to have to use a lot of fuels to even get the hydrogen?
So what you're asking is right there. You have this methane come in, you get hydrogen out, and you produce a lot of waste. Now it just happens that in the dorm that waste heat you capture it. So you get electrons, you get waste. So in the context of a dorm like this, it makes sense. You say, I'm not insufficient, but I'd like to still have waste heat. The way I know that can be done, probably with better catalysts in these field researches right now. There are also problems with locating these things, and it's very common. You don't usually having a tank in the basement. So that has to be taken. I'm not really interested in that.
So you think with these, for these catalysts might...
That has to be the hope of Honda. What if I had money? I don't think so. They're sponsoring research here, and to come up with a new catalyst to make that much more way less than that sort of thing. Ask you all something. Is this something that you find good idea? Yeah. All right, good. Listening, I talk to different audiences, and mainly just people that are involved in administration to money going. And now, okay, we're really running. When you talk about it, it says, yeah, this is how we do it. We should do it. And Stanford should.
Yeah. You talk a lot about how you want to be able to change the technology. I guess, I'm making a modular door. If you could just kind of put a new system in and, pull the old. It seems the infrastructure in the dorm is so into.
You're right. So what you have to do here, on this dorm, redundant examples for water reuse. Even if you get it right away, you're not going to go back and forth. But you want to have all that going in place. And the same thing for sensors, you want hardware as well. So you put both of them in. So that's how you do it. You put this in, you build it in now, and using it in the future. Those things are behind the walls, all that is. And that raises the cost from. But in terms of changing things, changing stuff takes place in the basement. What kind of water system do you have down there? You're exactly right. And the plumbing cost here is like a typical stress test wax. Because we're going to have, you would probably want to separate out wash water, you want to separate out water from urine, water from toilets, you may break water from the kids, for example, all the things say irrigation and flushing. So you've got to kind of plan all at the very beginning. Yes?
Would that be done on site, or would the water be taken to a large treatment plant and then back?
We do it on site and we do it with certain concepts that involve membranes, and get right there. Probably two stages of membrane bioreactor. First stage anaerobic, second stage aerobic. So in one stage you get a lot of methane, next stage you take out a lot of nutrients, and you produce a water that would be just about ready to run through a reverse, and then you can do anything with that water. Disinfect it, and then you can do anything with it. But after the used for all purposes except drinking, it's not going to be down somewhere else. It's going to be right there. Not too. Not that every house is going to have a waste. The problem here that we have is all of our sewage avenue out off the wastewater. They feel water that we can irrigation stuff is back the other way. Up there, and you got that water back up on water that would take a lot of energy. But we have here that places like the water treatment systems and water reclamation systems. So there's a lot of those. The future that you see right here are more small scale systems. You saw example of systems will probably the same thing.
A little bit more about in terms of we could improve understood how to is a way lower and also trap environment.
Only really I've never really used it, so I have a look at that, the membranes are looking at that kind of thing, meet performance standards, in terms of insulation and that. One of the things we would look at here is say, well, let's evaluate and see how they really, the temperature difference and, thermal conductivity across that. So you do some energy analysis and really working. There's a little bit of a funny deal with the green roof. If it works on a roof, it's a good job. It's really and they can be from a bunch of small high-power roofs to these sort of high-rise apartments. On the street, I saw this guy working on these buildings that was demolishing it. The house is kind of about this size. I was shoveling. It took me a minute to realize, what was this person doing? And what you have is a house with a wood roof and about 1 foot of dirt on top. It's not a green roof. That's the issue. You get some of that just put on a roof. Now, it wouldn't look so what we do. You say, well, it looks nice. Well, does that really make sense here in the summer to, put water up on a roof in the lower region? Maybe it would, maybe it would. Just the earth material itself will provide a lot of benefits. So it depends on how you want this whole thing to look. Do you want it to look like a bare spot, or do you want to look like maybe good garden or something like that? I don't know if I got some details to your question, but I thought I was trying to see what 1 foot of this place that was built over years ago.
I'll respond to that question. I was in the last year that did some scope of this. You got to realize a lot of civil environmental engineering firms are work projects. You mentioned more needs and working in fact. The student side, there's at least 2 this quarter they're working on the materials directly with people like that. They're looking in and study everything from scoping the vehicle or whatnot. So the way agreement, one, it is something that has been used nowadays. It's still a little conventional, though, sort of in the 70s. And now you've got mostly high-profile projects, like, of course, I believe corporate headquarters or factory building has several acres of green, and they do every bit of rain that comes on there goes percolating through the dirt, and it's pretty darn clean coming out. They can pump their own wastewater out there and do the same thing, and the water has to pay to shut that down the treatment plant. And the big concerns then also the other leaking membranes obviously building up field. It's been done. A lot of it comes down to, do you want just like a thin coating of dirt and a thicker dirt being laid? I was really excited last spring when we were doing your study. People haven't done that much work in it, but it looks this way. That you put a green roof on and then put solar panels on top of it. The roof contributes to cooling. It's the only thing you get that much water up there is going to get more heat in that part. And that's the case. We can start things together and all disseminate it.
Good. Thank you for that answer.
So yeah, there's a lot of chance for student involvement here that we cover in this presentation, but everything from our writing the major class to design experience, everything else is going through the green door. A lot of student involvement in the department. And if you want to talk to me afterwards, Lauren, whoever, we're actually looking right now for instance, plugged into all their outlets in the room and help your energy look very, very big. Photovoltaic on the roof. When you get power, by changing the course of the day. And then that determines, well, how to sell them back to the grid. Sort of volunteer there. I can get longer than that. And then we just check out the daily use patterns or 1 or 3 of the see. That's data we need to do the design of this world. And we're looking to help get that.
Any other questions? Well, you've all been very good.
Hey, how are you? Good, how are you? Yeah, it was good. Yeah, actually last night. Yeah, it was really good. What? I was really good. A little pear in my planner. It's pretty much, it won't be significant. Well, any updates? No, I'm gonna be, renewing my way, like, hopefully by next month. Good, yeah. It's open. Yeah, it's just, yeah, it was fine. I just didn't really know it was a tariff.
Word out. I think they love, like, someone breaking out of, like, this thing out here, like, they pull out.
Well, it will be a regular storm.
Involved in the environment.
EBS has a reputation, but that's mostly for aspects.
Yeah, EBS moved down the recreational topic. Call it environmental points. But it doesn't see it,
It's not quite for me.
Yeah.
So that was one of our objectives in the very beginning, safety for anybody. You just don't have to, so it's not a work, that it's just sort of back to nature or something.
What would students have to do with this?
I think everything that is the feasibility, we're scoping that out now, but yeah, I mean, the idea is basically to make it as fair as possible. Just have people live there and they're not going to backdrop. A lot of people have argued that, getting people to change their behavior, at least it tends not to happen. I'm concerned this is just the example that we keep bringing up because on top of all our minds is technology there, at least in the guys' bathroom, is waterless urinal. We use them in some places with permitting from Santa Clara County because of this. But the big thing is teaching that. No, don't put your great soap cleaner in here because the way the whole thing works is you've got an oil layer